This conference will now be recorded.
Okay. So before I proceed, guys, so do you all have any questions on any of our previous topics till date? Were you all able to follow how does linear regression work? How does logistic regression work? And how does clustering work? And I think we have spoken about, how you implement it in Python also. For linear regression, for clustering, we have done it. I think we have completed even naive Bayes. So how does a naive Bayes work, the predictive model? Any questions still here, guys, while you are probably going back and revisiting these topics? Anything that came up to your mind and you wanted to probably ask me? Is there anything? Okay. So I'll probably take it as a no. Okay. Okay. You're still looking into it and learning. Okay, Sanjay. Awesome. Okay. So I think then we can probably get started. So so the topic for today is, guys, it's basically our logistic regressions use case. Okay. So I was looking at, okay, what do we kind of kind of completed in probably in an hour and a half. Then I understood that the logistic regression use case is still pending. So I think we should be able to crunch this particular use case probably in the next 1.5 hours. But if it's going to take something more than that, of course we can borrow a little bit of time in the next week's sessions too. So the use case for today is basically on logistic regression, guys. So I think for linear regression, we saw a very simple use case, right? So we started off in Excel with basically that sales versus ads kind of a problem. Then we jumped into an insurance company's, that claims kind of a problem that we solved in linear regression. For naive Bayes, we had a beautiful SMS spam kind of a classifier model that we wanted to create. Then for clustering, we did market segmentation. We have done customer segmentation. And now one last pending topic, one last pending use case, which is basically for the logistic regression. We're going to be creating something called as customer response models, guys. Okay. So the use case that we're going to work on right now is very simple. It's called as customer response models. That's it. It's just basic campaign response models or customer response models. So you can call them as anything. So what happens is, guys, so today this is basically, this objective that we are solving is a very common problem. Okay. I see a lot of my folks, probably once into the job or something, a month or 2 months later, they come back with the same objective. And I just give them an answer, say, go back to this particular use case, review it, you have the solution at hand. So the objective is actually very, very simple, guys. I'll just define it in plain sentences. So the idea is simple. Say, for an example, you run a company. Let's say you're running an FMCG company. Okay. So the point is, there are a lot of customers with you. You have a massive customer base. Okay. So what happens is there are a lot of people who are actually buying. They are pretty loyal customers. But at a particular point in time, what probably you see is that a lot of these customers have been little inactive. Okay. Say for an example, I'll take an example of bank, something I'm very familiar with. So say for an example, you have something like a card you have, okay, like a credit card. So what happened is in a credit card, typically people who are activating the credit card within 3 months, right? They are the people who have been some pretty evergreen customers for a bank here. While any person was probably taken more than 3 months to activate that credit card, they're not so very active customers, which means there's not much that you can earn from these customers. They're not much of a value for us here. So most of the banks, right, they will try to do something. So they will, even before completing the 3 months, they may want to understand why do you think these people have probably not been able to activate within the first 3 months? Why is it that the other people are able to activate in the first 3 months? So can we go back and identify out of the people who may not activate in the next 3 months, to probably make them get activated by running some kind of a campaign here. So the concept is what? So I know that there are a lot of other customers who've been pretty loyal and they've been pretty active, but there is a certain customer base who are not so active. But I want to kind of understand, is there a probability that these guys can be activated by running, let's say, a small campaign or something like that? I can run a campaign, I can give them some discounts, I can do something. So you just want to understand that, okay, I have $100 budget that somebody has given to me. If I'm going to use up this particular $100, I need to make it the most efficient way. In the sense, I can't go back and run a campaign on somebody who may not even respond to the campaigns I'm going to do here. I need to go and shell out this particular money on people who have higher probabilities of probably responding to the campaigns here. So let's say, for an example, what happens with your food apps today, Zomato, Swiggy, etc. Why do you think that you get a promo code, but probably another person doesn't get it? The reason is because the other person might be a very loyal customer, but you're not so like that. You're probably using it today, but tomorrow you're forgetting it. So they still want to kind of make you a very active customer. So that's why they start giving you all kinds of promo codes and things of that sort, right? So the idea is very simple, guys. I want to go back and activate a lot of these customers. It is just that I don't know which guy to probably target. I want a predictive model to go back and tell me that, hey, these are the people who have high chances of responding to your campaign here, which means your campaign results are going to be much more effective if you run on these people rather than shelling out some money on somebody else here. That's it, guys. This is basically the objective at hand. So the bank thing I told you, right? So this is one of our student who was working on it. So he wanted to go back and check this one. He wanted to understand that, hey, so previously we gave all of these campaigns to a set of customers. They did respond. Now I want to go back and check in near future if these are my customers, on whom should I probably run the campaign here so that I get the maximum benefits out of it. So it's a very common problem, guys. You can see it everywhere. FMCG companies, let's say banks or any industry that you probably take, right? This is going to be a very common use case, I'll tell you. Okay. So you just want to go back and understand what is going to be the probability that a particular customer might respond to a campaign. You want a predictive model to do the job rather than you manually choosing these customers based on your intuition. You're going to leave it to a predictive model to do that particular thing. Okay. I'm sorry, guys. Okay. So this is basically the objective at hand, guys. So what we have with us is we have the historical data about which of these customers have responded and which of these customers have not responded. Okay. So just give me a second. Let me quickly open this particular data set. Okay. So you can see here. So this is a data set that we have at hand, guys. Once again, it's a bank's data set. Okay. It's a pretty beautiful one to start working on. So what this bank is actually telling us is they're saying that, there are a lot of customers with me. Okay, I wanted to run some kind of a campaign and kind of make them activated. Okay, but he sees that, he has probably run the campaigns on what? Somewhere around 41,188 people. So how many people are there? 41,188 people. Out of all of these people, not everybody had basically responded to the campaign. Basically, the target variable is, did they come back and open a deposit account or not? Okay, they're running some kind of a campaign. Okay, so the result of the campaign is, if the customer is opening the deposit account, then it means yes, it's a success. The campaign has proved to be very, what I would say is, positive. While if the customer is not opening a deposit account, it means the campaign was not a very massive success here. So you have all of the profiles. You basically have the profile of each and every person. So you know what is the age of the person, the job of the person, what has been the marital status, what has been the education that he is going through. Okay, does he have any kind of loans which are in default? Is he having any housing loans currently? Yes or no? Or are there any other kinds of loans that he's probably having? While doing this campaigns, did you contact the customer on a cellular phone or on a telephone? When did you campaign? Basically, it's in the month of April, August, December, January, March. When did you do it? And which day of week did you do it? Did you call him on a Monday, Tuesday, Wednesday, Thursday, or a Friday? So what has been the duration of this particular the call or this message that you probably had with them? So this is basically the duration that you can see here. Okay, I think the duration is a little bit different. We'll go back and look at the dictionary. The campaign is the previous campaign, I think. How many days has it passed and all? We'll jump into the dictionary. I'll do it. So previous days, then previous campaigns outcome. Okay, we have all of these things. We have a couple of macroeconomic variables also. Okay, we have something like what has been the employment rate, what is the consumer price index, what is the consumer's confidence index, what is the Euribor rate for a 3-month period, what is the number of employed people in this organization. So I think these are the different kinds of variables that is available with us. So the data set is saying, hey, these are the different variables I have at hand. So make use of this and now tell me why did certain customers did respond to the campaign and why did certain people did not respond to the campaign. So we are measuring the success of a campaign based on whether did they open a deposit account or not. If they have opened it, then it's a successful campaign. If they have not opened it, it's not so successful campaign here. Okay. So this is the objective, guys. To keep it very simple, we have a historical data about what has been the results of campaigns. Why do you think people responded? Why do you think people did not respond? Rather than leaving it to intuition or anything else, which can go back and select the customers to be selected for the campaign, what you're going to do is you're going to leave it to a predictive model to do the job. So the predictive model is going to handpick saying these are the customers that you should be probably targeting. Okay. So rather than leaving it to your intuition or any other kind of business strategy, guys, we're going to leave it to basically a beautiful predictive model in this case here. Okay. So if you've all followed what is the objective, what we can probably do next is we can quickly jump into the data set. Okay. Let's look at the individual variables importance. Sorry, meaning. So the first variable is basically the age of the person. Second is the job of a person. Okay, is he in an admin work or is he blue collar work or is he an entrepreneur? Is he a housemaid, management? What kind of a work are they probably into? What is the marital status of the customer? Single, married, divorced, unknown. Okay, what is the marital status here? Education, basic 4-year degree, 6-year degree, 9-year. You have high school, illiterate, professional courses. Okay, then you have default. Does the customer have any other existing loans which is in probably default? Yes or no, or probably we don't know any, we don't have any information about it. Does he have any housing loan? Yes or no, or unknown. Does he have any other kind of personal loans? Yes or no, and unknown. These are the possible values. So these are basically the bank's client data. This is the client data that was shared with us. Next is, there are a lot of features which are related to the last contact of the current campaign. So you're doing this campaign, right? While doing the campaign, what was the kind of behavior of the customer during this particular campaign that was run? So the first is the contact method. Did you contact the customer on cellular phone or was it a telephone? Then on which month did you call him? Which day of week did you reach out to him? What was the duration of the last contact? It's in seconds, which means we did the right thing. So it was basically the duration of the last contact. So did he speak for 10 seconds or probably for, let's say, 60 seconds or 3,600 seconds? So how many seconds did he probably speak on the phone? That is what we have here with this variable number 11. Then we have a couple of other attributes like, how many number of contacts were performed during this particular campaign for this client. How many times did you probably contact him? Then P days is nothing but the number of days that passed by after the client was last contacted from the previous campaign. Okay, so the number of days that has passed after the client was last contacted from the previous campaign. So what was the gap between the previous campaign versus the today's contact that you're doing? How many days has it probably passed? Hope you're not troubling your customer every minute. Then certain other attributes of the previous campaigns that happened. Okay, not the campaign that we are having here. It is one step even before it. So in the previous campaign, how many times was the client actually approached? So the number of contacts that was being performed in the previous campaign for the same client. So you have that number here. What was the outcome of that previous campaign? Was it a failure, non-existent, or was it probably successful? Apart from that, we have certain macroeconomic variables like what is the employment variation rate, the consumer price index, consumer confidence index, the Euribor rate for a 3-month period. Then we have what? The number of employees that you have employed in this quarter. So you have all of these variables, guys, and we've also recorded if the customer opened a deposit account or not, or a term deposit account or not. So the success of this campaign is being measured by the customer is opening an account. So only if they open an account, you get money, you can lend out loans, or you can invest somewhere. So you need more and more deposits, right? So the question is, did the customer open a deposit account or not? Yes or no? That's the question we are asking. So we have the historical data about whether they have responded or not also. Now the work for us is pretty simple. We just have to create a predictive model which will try to correlate these predictive variables with the target. That's it. We just have to analyze. So what is the effect of each and every variable here on the target? With that, you're going to create a predictive model. And tomorrow you may say, okay, I'm likely to contact a customer whose age is 20, who's in this job, his marital status is so and so, education, etc. is so and so. The last campaign results were so and so. Today's MEVs are so and so. Can I expect him to open an account or can I not expect him to open an account? So you're doing a predictive model already. Then you're asking the predictive model. You're doing a what if analysis. Hey, what if it happens like this? Will the result be like this? What if the client was having certain features like this? Do you think he's more likely to respond to the campaign? That sort of a question is exactly what we're going to ask next. But the first step is basically creating the predictive model, understanding the importance of each and every driver that you see here, how do they impact, and you're going to create a logistic regression model with all this intelligence built on the inside. So once the model has been created, as I just told you, all right, so you can just go back and ask the question, okay, saying, hey, what if in case my customers are like this, what is likely to happen? That's it. Okay. So what we do is, guys, so as usual, we need to go back and import a couple of libraries for a usage. First is it's going to be OS, then it's going to be NumPy, it's going to be pandas, matplotlib by .pyplot.spa. So these are the 4 packages that we will need by default all the time. NumPy as NP, pandas as PD, matplotlib.pyplot as PLT, and import OS. So now you guys can see I'm changing my working directory. We are checking if the working directory is right or wrong. Looks okay. So what are the steps that you need to follow? I think we have been discussing in all our classes. The very first thing that you need to do is, of course, you need to import your data in the right fashion. You need to do some data modelings and all if it is required. That is merging different files, etc. if it is required. Number 3 is going to be data quality checks. So you're going to check if the data quality is perfect. Are there anything that's missing? Are we doing some errors while probably importing or doing some data models here? So I think it's a single file, so not much of a problem for us. We're going to go back and read this particular file. Let's look at the type of data. It has got imported as a data frame. Looks cool. Let's look at the info of it. So he's saying age is integer 64. Looks fine. Job is object. marital, education, loan, contact, month, day of week. All of these people are of an object data type. Looks completely fine. The duration of the call, the campaign, number of times you have basically contacted them, how many days has it passed, the previous outcome, all of these are integer 64. Once again, I think it seems okay. Previous outcome result, that is an object. Of course, I think it was failure, success, etc. Being an object is completely all right. Employment variation rate, consumer price index, confidence index, Euribor for a 3-month period, number of people employed, floating 64 is completely fine. The target Y being an object, once again, this is also totally fine. So the data types are all completely okay. I don't think there's something that's going wrong. I don't think we need to go back and work on them. That's completely good. Are there any missing values? I don't see any missing values at also. Everybody is what, 41,188. Everybody is perfectly same. We can once again just check it by running this code pd.disneyofdata.sum. He's telling us no, there are no missing values any of these columns here. Looks perfectly okay. So the data quality check first we are doing is we are checking for NAs. We are checking for variable types. We can check for infinities. You can check for nulls. Any other special values which the models can't understand, right? You need to work on them. So we have done all these things. It looks completely okay. So the basic data quality checks is completely okay. It's basically passing. The next thing that you need to do is you need to check if there are going to be duplicates in the data or not. And I think we had this in one of a use case, right? We had certain duplicates. So we are checking if there are any duplicates or not. So it's checking each and every row and it will give you true and false result. We'll ask for a sum of it. We do see that 12 of these records are basically a duplicates. 12 of these records are basically duplicates right now. So what are we going to do? We are saying data got duplicated. Wherever it's true, it's a duplicate. Wherever it's a false, it is not a duplicate. Now we just have to invert the logic. Wherever it is a duplicate, it will become what? False. Wherever it is not a duplicate, it will become true. So hence using a tilde symbol at the front, and we're going to invert the logics right now. And it's only the true people who will get subsetted, or basically the people who are not duplicates will be subsetted. So now I think you should end up with 41,176 records. So what do you see? 12 records have been removed. Previously we had 41,188 records. Now we have 41,176 records. Step number 1 that we'll have to do here. Okay. So we are checking if there are any missing values or not. I don't see that there are any missing values. If there were any missing values, how can you probably handle it? I'll give you a methodology, guys. If it is a numerical column, okay, please impute it with the median of the column. Okay. So say for an example, you have a column, okay, and you have like 100 records, but 2 of the records are missing values. So what you can do with the rest of the 98 people, you can find the central tendency with the median, and then you can impute that median in place of those 2 values there. Okay, when it's a numerical column, median is the most suitable thing, guys. Okay, you know that mean versus median. Mean is what? It's more, what I would say is affected by outliers, right? Whereas median is somebody who's a little more robust to outliers. That's why we typically use a median over to a mean. Similarly, if it were a categorical column, you're supposed to use the mode of that particular column here. Okay. So if it were a categorical column, guys, please use the mode of that particular column. Example, you have a column something like gender. You have 100 records, but 2 of the records are probably missing the gender. So you just have to go back and find which gender is probably occurring the most number of times and go back and impute that value in those 2 places. So this is one of the easiest methodologies we do. In fact, I think people call this as a rough fix. Okay, the name is in fact called as a rough fix. It's a very rough fix that we're doing. It's not very statistically sound and all, but still it's okay. But taking certain predictive models like XGBoost and all, what they will do is they'll consider the missing values as a separate population itself. That is, records which are having missing values, right? They will become an entirely different population itself. That's another methodology of handling them. Or you can even impute values like minus 999 in your data set. Once again, the same concept. Minus 999 is an extreme value that you don't see very often, right? So when do you see minus 999 in a data set? I don't think it's pretty common, right? Positive 999 at least is okay. The price of products, what they don't do it at 1,000, they say it as positive 999. But a number like minus 999, right? It's not a very common number. So wherever there are any values missing, people even impute it as minus 999. The reason is because if it's going to be minus 999, these records will be considered as a separate population. The model is going to think that these records are a separate population. They're completely different from the other people. So this is another methodology of doing it, guys. Examples are predictive models like XGBoost, which we will discuss very later in our sessions. We have something called XGBoost, extreme gradient boosting. Models like these members, they will use a value like minus 999 in place of the missing value. And then what will happen is the people with minus 999 as an answer, they will be considered as a separate population itself. So these are the certain things that we typically do, guys. Even we can drop the records. Even that is another way of doing it. You can even drop the records. Sometimes it may not make much of a sense to impute values here. So say for an example, today morning, I was just playing with the small data. Okay. So once again, it's a bank's data. So I thought of creating a simple feature like this. Okay. There was one feature which spoke about the total income a customer is actually earning. And there was another feature which spoke about the number of children that he had. It was basically a probability of default model that I was trying to create. I saw this two variables, okay? So what I wanted to do was, I wanted to find income by children ratio, okay? So my concept is that, if he's going to have more number of children, the income is going to get divided, which means he'll have higher expenses. He may not be able to repay the loan back properly. So the loan might probably go into a very troubled state. So there what happened was, so income could have been $1,000, but certain members, they would have been single, so the number would have been 0. That is, the number of children would have been 0. Or even for some people, it would have been an NA. Okay, for some people, it's going to be an NA, while for some people, it would have been a 0. So what is going to happen when I divide 1,000 by 0? Answer is going to become infinity, right? Or if I have NAs, 1,000 by NA, it's going to become an NA. So I was just thinking, okay, what should we probably do? In place of NA, should I keep it as 0? So keeping it as 0 will once again end up as infinity. Okay. Then I just thought, okay, then using median, would it be the right thing to do? Obviously, no. Because I saw that some of these people have had what, 7, 8 children and all. The keeping the median was somewhere around 4, 4.5. So I can't say that probably a person who's single will have 4.5 children. Right? It doesn't make sense at all. So rather, it would have been much more better if you had kept NAs as 1. Or in place of zeros also, you could have just kept it as 1. So what I actually did was, I replaced NAs as zeros. Then I just incremented everybody by 1. So zeros will become 1, 1 will become 2, 2 will become 3, 7 will become 8, 8 will become 9, and it'll keep going on. So now I won't have both the issues. I can't, impute with median because it will not make sense. And similarly, I can't probably keep it as 0 because it's going to divide it and give us infinity as a result. So I just thought, okay, let's replace NA as 0 for now. Then we will just increment it by +1, which made more sense. Then it was completely okay. So a guy who's earning $1,000, who's having no children, right? 1,000 by 1 will give me 1,000 as a result, as it is. But a guy who's having 2 children, so 1,000 by 2, we are going to say $500 he's going to reserve it for his children, while $500 he's going to keep it for me for paying back my loans, which made sense. Okay. So I'm just telling you guys, this is a very rough fix. You can't really rely on it on many a times. Luckily, you can see like today morning I had an example I was able to tell you guys. So you can't really rely on all of these methodologies. You need to leave it to a little bit of your intuition also at many a times. Okay, sometimes keeping it as 0 would have made sense, keeping it as 1 would have made sense. So depending upon the use case, the variable that you're handling, please make use of the right methodology. Okay. So just letting you all know, if there's going to be any missing values, these are the things that we need to do. It's called as a simple rough fix. Okay. So what we're going to do next is, guys, once the data quality checks are done, once you're fine with your data, everything has been solved. Now is your analysis, especially something called EDA, which, as you all may know, it's called exploratory data analysis. It's called as what? It's called as exploratory data analysis. You're basically going to go back and ask a lot of questions to the data. Okay. So we're going to ask a lot of questions to the data. We are asking him, hey, is there any unique things that happening within the data which I can probably use as a variable in the predictive model, a sort of a feature in the predictive model? Is there something that's really peculiar? Is it something not so common that's happening? If the model is not able to capture it, I will make sure that I explicitly ask him to capture it. So exploratory data analysis is basically a phase where you go and start looking into the data in a very deep dive fashion. You're going to start asking a lot of questions to this particular data here. So what I will do is, guys, I'll just keep it simple and we'll do it for a couple of variables on how you should be exploring these variables. Under the EDA, the very first thing that you should always do is look at the target variable. I hope you all remember. In linear regression, I told you, right? The very first thing that you should always do is please observe your target variable. Why? If the target variable is numerical, you may want to probably understand the distributions and all, because understanding the distributions and working on top of it will give you better results. Or if it is a categorical variable, once again, you need to look at the frequency distributions, because they will help you understand a problem, something called a class imbalance problem. I hope everybody remembers it. We had it in the spam classifier model, I think. We have something called as a class imbalance problem. So you need to check and understand if the number of samples for either one of these classes, right, are they basically the same? Is it probably not so skewed? If it is skewed, then I call it as a class imbalance problem. If it is not skewed, then I see that the data is completely okay. So this is the first thing that you need to do. You need to look at your target variable here. What is a target variable we have? We have a target variable which is y, which is whether the customer had opened a deposit account or not. So let's go back to Python. We're going to ask this question here, okay? So we are saying, hey, data, I want you to give me the y column. Sure, why not? I want you to give me the counts. So he says the number of yes is basically 4,639. The number of no's are basically 36,537. Now we're going to divide it by the total. The total is 41,176. In terms of percentages, we can see that the number of samples for no is 88 percentage. The number of samples for yes is 11 percentage. There are 89 percentage samples available for no, only 11 percentage of samples available for yes. Recollect back to the spam classifier problem. What did I tell you all? If you have something like this, a class imbalance problem, there's a very, very high chance that your predictive models might start favoring the class which is present in abundance, isn't it? What is going to happen? Your predictive model is going to start favoring, or it's going to start predicting too many of the class which is present in abundance. which means my predictive model will start predicting more number of no's and very less number of yes. So what is going to happen? You're basically going to miss out on a lot of people who are having yes as a value, and you'll start predicting that these guys are probably no. I don't think they're going to respond, but probably they might have responded. So this is called as a class imbalance problem, guys. Okay, it's a very, very important thing to notice. So class imbalance problem is a very, very important thing. You need to understand this one. If you know that one of the set of samples are present in abundance, your predictive models are going to become more biased towards those classes. Okay, he's going to predict more yes and very less number of no's right now. That's what is called as a class imbalance problem. So the way we're going to solve this class imbalance problem is two methodologies, guys. I'll tell you the two methodologies, but I would prefer you guys do the second one. The first methodology that we typically use is a sampling technique. So what do? You typically do something called as a sampling technique. So what do you mean by sampling? Basically, I'm going to go back and create a lot of new data points. I will try to upsample this yes and make sure that both the people are 50-50, or I will downsample the no and make sure that they're going to become 50-50. So upsampling will give me probably what, 80,000 records or something, while downsampling will end up with what, 20,000 records or something even lesser. So sampling technique is one of the most popular things that you can do. Okay, so what are the different samplings you can do? You can downsample the no, you can upsample the yes, or you can do something called stratified sampling. Basically, the concept of stratified sampling is that you're not going to use this entire data, okay? You're going to randomly sample 50% from here and another 50% from here. I mean, the meaning I'm telling you is, say for an example, if I know that yes is basically 4,639, the yes here, right, 4,639, these people will be retained as it is. From the no alone, right, what will happen is he'll pull another 4,639. So now you end up with 50% and 50%. So the concept of stratified sampling is, it comes from a word something called strata. Okay, so the concept of stratified sampling is that the ending up data set post my sampling, right, I should be ending up with basically the target with equal distributions of yes and no's. That's it. So what is he saying? He's saying stratified sampling is a technique where I'm going to come up with a new data set. In this data set, I'm going to observe my target, and the target I would be probably ending up would be 50% and 50% for yes and no respectively. Okay, so this is the point, guys. Stratified sampling technique is a place where it will try to observe the target and will try to kind of equate the number of people in all the classes. So all the classes, are they having equal number of members? That is what is called as a stratified sampling technique. So you can use either of these. You can use downsampling, you can use upsampling, you can use stratified sampling who will do the work for you, or there is even another sampling technique, something called SMOTE. It's called as synthetic minority oversampling technique. It's telling us what? In a very synthetic fashion, the minority class, I'm going to oversample them. SMOTE. Synthetic minority oversampling technique. SMOTE. What do you exactly mean by SMOTE? What is this sampling technique actually telling us? Very simple, guys. Let us go back one step backward. Okay, we were doing our data quality checks, correct? What are the data quality checks we did? We checked if there are NAs available, if there are any infinities available, or are there any nulls available, or are the column data types getting imported properly or not? The third one that we did was what? We wanted to understand if there are any duplicates in the data or not. Why do you think we removed the duplicates? Very simple. Say for an example, if this is one point, this is another point, let us assume this is another point and this is another point, okay? What do you mean by duplicates? It means, so I have a dot here, right? I can see that this is probably having a certain value of x1 and x2. I will have a lot of people who are actually overlapping on the same place itself. I'll have another person at the same place. Then I will have another person on the same place on top of them. Then I'll probably have even another person on top of them. So the point is that, guys, if you look at all the four people, they're all having the same x1 and x2 values, right? They're just sitting on top of each other. So the first guy is sitting on top of the second guy, then the third guy is sitting on top of him, the fourth guy is sitting on top of this guy. It actually provides no meaning at all. It is not at all helpful for us, guys. No way it is helpful for us. It is actually the same person. He's getting duplicated. So the same person is entered to the model again. You are saying, hey, he has got predicted properly. Let us just come back outside. He literally serves no purpose at all here. So what is going to happen? Let's say something like a logistic regression model when he's working, right? So the square goes in. Am I getting predicted properly? Yes. Okay. Star goes in. He says, am I predicted properly? No. So the logistic regression model will go through a change. The triangle will then go on the inside. Am I getting predicted properly? No, you're not. He will go through a change. Then one point will go. Am I getting predicted properly? No. The logistic regression will change. Next point will go. Am I getting predicted properly? Yes, you are. Next point again. I think it's the same duplicate. Of course, you are getting predicted properly. Another duplicate. Of course, you're getting predicted properly. Why do you want to keep coming back and checking me again and again and again? So the point is that, guys, this is actually serving no purpose at all. Duplicates are literally doing nothing. They do nothing. When the first data point is going inside the model, right, to get himself trained, there itself the work is done. The rest of the three people are merely just checks. They're just checking, hey, have we got predicted correctly or not? That's all. They literally serve no purpose at all, guys. That's it. That is exactly the reason why we are removing the duplicates in the data. So if I keep the duplicate and I create the predictive model, I will get a certain coefficient. If I remove the duplicate and create the same model, I'll get the same coefficient. It is literally doing no job for us here. It is doing zero work for us, actually speaking. Now, going back here, guys, see here, I told you that we have a class imbalance problem. What can we do? We can do a downsampling. What do you mean by downsampling? I can basically just choose what, for 4,639 number of no's. So what will be the problem? So if you see here, the problem is that the number of no's we had was 36,000 something, right? So we had 36,000. The number of yes we had was 4K. If I downsample, what will happen? 36K people will not be used, only 4K people will be used. Here there is another 4K, a total of only 8,000 data points we have, correct? So when I do downsampling, what are you ending up with? 36,000 records will become 4,000 here. These 4,000 are kept as it is. You just have 8,000 data points in the total. So what is the problem of doing a downsampling? Loss of data. You're losing a lot of data. There are what, 36,000 samples. When you take only 4 of those, 32,000 samples you're losing. There's a lot of loss in data. This is problem number 1. Why you can't do a downsampling technique. Over to number 2. What is number 2? Upsampling. So basically you're saying, hey, let the nose be as it is, 36K. While the yes, right, we will make duplicates and we'll make it as 36K. How much are you ending up with? 72K data points. So number of data points have increased. I'm very happy. But the problem is you're actually just increasing your computation, you're gaining nothing. Why? We just know that using duplicates in the data is literally serving no purpose at all. It's a complete wastage of time, isn't it? So what are you saying? I have 4K data points. So 1, 2, 3, 4. I have 4K data points. You're making duplicates of all of these people overlapping on each other, right? So 4K points, everybody is having what? Somewhere around 8 duplicates for each other, isn't it? Approximately 8 or something, right? 8 or 9, whatever it is. You're having an extra 8 people who are duplicates for you. It is literally doing nothing. So upsampling right now is also actually speaking as a problem. It's literally serving no purpose at all for us. It's just increasing the number of duplicates, but it's no value add at all for us statistically here. That is exactly when there are a couple of people who proposed something called as SMOTE. It's called synthetic minority oversampling technique. It's called as what? It's called a synthetic minority oversampling technique. So he is saying, in a very synthetic fashion, I'm going to oversample these minority people. That is, he's saying, say for an example, if the square is actually speaking your person whom you need to upsample, don't create a perfect duplicate. SMOTE is saying, let's create duplicate by adding a little bit of values here and there. So he's saying, hey, I'll increase the x1 a little bit. Hey, I'll increase the x2 a little bit. I'll reduce the x2 a little bit. So I'll play with the values of these people and I'll start creating a lot of data points in the surrounding region itself. Now seems to be very good, isn't it? So say for an example, this square, right? Let us assume the square is nothing but a person whose age is something and probably something else is something. Okay, so his x1 value is what? I'll assume something like 50. X2 value is something like 30. Now I'll create a data point which is 51, 30, somewhere here. I'll say 51, 30. Then here I will say 50, 31. Here I'll probably keep as 50, 29. Here I'll keep it as 49, 30. So I'll just decrease or increase these columns and these values a little bit up and down. I'll be able to create a lot of duplicates surrounding this particular guy. Beautiful technique, isn't it? So he's just saying, I'm going to introduce a little bit of, error or a little bit of noise to the data. So after inducing a little bit of this noise or an error, you can see that these points will not be perfectly overlapping to each other. They're going to be little what scattered here and there. Now this looks okay. This looks fine. So these are basically people who are very similar to that existing square. Now this looks okay for me. So this is a very, very beautiful statistical upsampling technique, guys. It's called synthetic minority oversampling technique. But I don't think it is available in regular Python and all. Probably, I think it's available in stats models. In this package, I think it is there, SMOTE, if I'm not wrong. In stats model, I think it is there, but we don't really see many people using this one, practically. Okay, so this one is good. You can increase your data set size and all. This is one way of doing it. You can come up with an SMOTE sampling. One is doing this itself is going to be a headache, and you end up with a bigger data set once again, which will be another headache. So this is one methodology of solving it. But I have another methodology for all of you guys. Another beautiful thing I want you all to do is basically go and keep something called class weightages. That's all. You just have to keep something called class weightages. That's it. What do you mean by class weightages? Very simple. Now we are saying for no, you need to give only 11% weightage. And for yes, you need to give 88% weightage or 89% weightage. So previously what happened? Because of the data set size, the no members, they were basically what, 89 percentage. The yes people were basically only 11 percentage. So the size of the data set made some changes to the importance in the model. The model will start giving 89 percentage importance to no and 11 percentage importance to yes. Now all you're doing is you're saying just reverse the signs. You're saying 11 percentage to no and 89 percentage to yes, which I will tell you guys will kind of get nullified by this guy, by the data set. I mean, they'll kind of cancel out each other. They both will end up with 50-50. That's what I'm saying. So data set is calling in this direction, while the model is telling let's go in this direction. Both of them will, kind of cancel each other and they will become 50-50. That is what will happen. So you can see. So this 89 plus 11 percentage the model is saying, while 11 is told by data and 89 is told by model, you can see it will become 100 and 100. Right? Actually, you're ending up with equal weightages for both the people. That's what is happening. So dataset says, let's give more importance for no, while model is saying, let's give more importance for yes. Both the people will cancel out each other, actually speaking, intuitively. So both of them will kind of have equal importance right now. Yes will have the same 50, no will also have the same 50. So what do you mean by this class weightage? If you ask me this question, guys, it's very simple. When you create a logistic regression model, right? So when we come down here and we create the logistic regression model, so you can see that in the logistic regression model, there'll be a variable something called class weightage. Okay, so just give me a second, guys. I can quickly open. So scikit-learn logistic regression. Look at the documentation. He's saying scikit-learn or linear model or logistic regression. You can see there is something called class weightage, right? It's available in both R and Python, guys. That's the beautiful thing. He's saying class weightage is something that I can do. What do you mean by a class weightage? Let's read the help that he's telling us. You need to come down here. Okay. So he's saying, I want the weights in this particular format, which is what is the label and what is the weight I will have to give. Okay. If not given, all classes are supposed to have a weight one, but that's not actually happening because of the data. Okay. So what he's saying is, note that these weights will be multiplied with the sample weight if the sample weight is specified. Okay. The balance mode adjusted inversely proportional. I don't think he's giving us a very good help of what's happening. Okay. So I'll tell you what's actually happening at the back end. If you give a weightage, right? So you're saying no will probably have 11 percentage weightage. Yes will have a 89 percentage weightage, right? So the meaning is that, guys, if let's say I have one sample who belongs to the no category, okay, the amount of error that he had would have been this much. Okay, so this is the error. If I have a point like yes who is getting misclassified, ideally the error should have been something like this. But since you're saying 89 percentage importance, the error will be blown up something like this. So what will happen? Basically, guys, the error component that you have, right? The error that you get, the error for misclassifying a no and the error for misclassifying a yes, the error that is coming out of a sample of a no who's getting misclassified will be suppressed, and the error coming from a sample whose value is yes, and when he is getting misclassified, his error will be blown up. So the error coming out of a sample whose value is no and he has got misclassified, his error will be suppressed, guys. It will basically be brought down, which means if I have an error of 10 units, right, it will be brought to 1 unit. While the error for misclassifying a point with a label of yes, if his error was 10, now it will be blown up by 100. So what do you think will the model start doing? the model will make sure that he doesn't misclassify this particular yes here, because the error is actually becoming bigger and bigger. So he says, hey, forget the no's. The amount of error coming from those people are basically getting shrunk, while the amount of error coming from these people are getting blown up. So the model is saying, yeah, I think it's better that I give more weightage to the yes and lesser weightage to the no. So what's happening? So the model is saying the errors that we are getting by misclassifying a no is getting lesser and lesser, while the error that we're getting for misclassifying the yes, right, is getting blown up so much. Let us make sure that we are not misclassifying the yes. Let us not worry about what's happening with the no. That is exactly what he's telling us. So the data point is telling you, or the data set is telling you to do what? Give more importance to no, less importance to yes, because they dominated the size of the data, while the model is saying less importance to no and more importance to yes, because the error is getting blown up bigger here. This is exactly what we're doing. By keeping a class weight, we are asking our predictive model to blow the error bigger for misclassifying a yes and shrink the error for misclassifying a no. So what will happen? Your model is going to tell you that, hey, I think the error is getting bigger and bigger, boss. Who is causing this? I think it is these people who are having yes as the label who are causing us. So let us go and make sure that these people are not getting misclassified right now. So what's happening? He is more, cautious over the people who are having yes as a label. He's going to make sure that these people are not getting misclassified. He's more and more cautious in this particular area here. So this is a much more better methodology of handling a class imbalance problem, guys. So the problem is that you don't have to do a sampling, right? Unlike in all the previous cases, you just have to say class weight is equal to what and what. That's all. The model will handle it at the back end, right? You're just blowing up the error or shrinking the error based on the weightage you're saying. That's it. So it is far, far, far better in fixing class weightages rather than using sampling techniques, guys. It's very good that you use class weightages, which is very simple, not so computationally problematic. Conceptually, you can explain it to people. It's so simple. So it is far, far better compared to sampling techniques, which are another alternative for solving the same class imbalance problem here. So I have never done these things. I tried SMOTE and all, but it has never worked properly. But class weightage, of course, it has worked tremendously. Okay, I will tell you guys, creating model without class weightage and with class weightage. I'll compare it and I'll show it to you even. With class weightage will perform better. Without class weightage will not perform so good. I can help you guys compare it also. We'll do it in some time if time permits for today. We can compare it and also see how the performances are working. Okay. So this is the EDA's first step, guys. We are talking about the target variable. Understanding the distribution of the target variable is very, very important so that you diagnose a lot of problems that may come in near future. So most people would have checked that these things are probably happening, and probably they won't even realize that that's why the model is actually performing bad. Now you should realize that even before I do such a mistake, now I've corrected for it. Right? I have corrected for the class imbalance problem by keeping a class weight. So you guys should not make that particular mistake. Okay. So tell me, guys, does it make sense till here? Importing the data, doing some data quality checks, doing your EDA on the target variable. Does it make sense till here? What is class weightage? What is class imbalance problem? What are the sampling techniques you've spoken about? Does it make sense, guys? Convinced till here? Okay, perfect. Okay. So This is the first step in your exploratory data analysis where you're trying to explore your target variable for possible anomalies or possible problems in the near future, correct? Since it's being a target variable, you will have to look at, sorry, target variable with this categorical nature, you need to look at the frequency distributions and all, understand if class imbalance problem might be a certain issue you may face in the near future. How do I probably handle it? That is exactly what we've done till now. So the next step that we're going to do is, guys, let's discuss about more categorical variables, shall we? So let us jump into something called education. I have something in education, okay? So let's jump into the variable, something called education. So we have it here. So we're taking up the education variable and we're looking at the value counts, basically the frequency counts. So what you guys can see here is that education is a categorical variable. It's a predictor. What is he? He's basically a predictor. So when the categorical variable is a target, you need to understand and solve for a problem, something called class imbalance problem, correct? If it is a predictor, guys, you need to solve for a particular problem, something called cardinality. What are we talking about? We're talking about something called as cardinality. What do you mean by cardinality? I think you might have come across this word, something called cardinal variables. What are cardinal variables? Categorical variables. What do you mean by cardinality? Basically, the number of categories present in a particular categorical variable is called as cardinality. So I have a variable whose cardinality is equal to 5. I have a variable with cardinality 10, cardinality 15, low cardinality, high cardinality, right? So typically what happens is that, guys, if you have a predictor variable with high cardinality, so what are we saying? We're saying, hey, I may have a predictor variable who's categorical in nature. He'll have high cardinality. So the definition of high, very approximately, I'll tell you guys, 15 categories, anything above 15 categories. It's once again a very approximate version. It may come to 10, 12, 13, any number, but 15 is something that people practically follow. Any predictor variable who's probably having more than 15 categories within himself is called as a high cardinal variable. So what is the problem with that? The problem is pretty simple. In certain predictive models like decision trees, right, the max is actually designed in such a fashion that they will start, splitting apart, or I would rather call it as they would start using up the variables, or they would think, or they would probably get biased towards predictor variables which are probably of high cardinality here. So what is going to happen? Predictor models, something like decision trees, right? So the concept of decision tree is basically I'll keep dividing my data set into small chunk. If I have 15 categories, he's the first person I will basically start splitting, isn't it? He becomes my natural choice. The concept of decision tree is what? Yeah, I have 1,000 data points. I want it to basically generate small chunks. Many chunks, small chunks, which are all what? Very similar to each other. If I have a categorical variable with 15 categories, if I divide using that variable itself, I'll end up with 15 chunks so easily. One variable gives you 15 chunks so easily at the first level itself. So this is a problem, guys. Even though the variable has not been so important, but mathematically there has been a flaw. So what happens is predictive models like decision trees will start favoring predictor variables of high cardinality in nature. So what is going to happen? Predictive models like decision trees, they'll start getting biased. They will tell that, hey, these are the people who are very important. They'll start factoring in these predictive variables who are having high cardinality, even though they may not have been a very good variable for us. Example is ID card of the person. We don't send ID card of a person into models like logistic regression. Why? Because logistic regression model will say it's redundant. We don't do it to a decision tree. Why? Because it'll start splitting using each and every person's ID card number. That's all. So that's why Do not use predictor variables which are having high cardinality, which is categories above 15. That's why you can see here. I know education is a categorical variable. We are looking at him. How many categories is he probably having? 3, 4, 5, 6, 7, 8. I think it's okay. 8 categories are okay. 8 categories is completely fine. But if I still want to kind of reduce it, I'll use my business knowledge. So I'll say, okay, 4-year and 6-year, they seem to be very close. So you can combine these two people. You can say 4 to 6-year. So instead of 8 categories, now you will have 7 categories. Then you can say, hey, a 9-year and a high school might probably seem very similar. You can compare and combine these two people together. So using the subject knowledge or a business or a theoretical knowledge, we can combine the categories here. Or another methodology is by using something called as weight of evidence and all. Okay, we have a concept to discuss. We'll be doing it in the next class. We have a concept of something called weight of evidence or information value that we can use up. So using this weight of evidence or information value also, we can find which of these levels are pretty similar to each other. Then you can combine the people who are very similar and you can reduce the number of cardinality. So you may not be able to drop the variable itself completely, guys, but you can treat it at least. You can try to reduce the number of levels based on your subject knowledge or based on certain statistical fashion. Example is a WOE, something called weight of evidence and information value. So you can probably make use of that thing also. Okay. So this is the point, guys. So looking at a predictor variable who's of a categorical type is also equally important because high cardinality is a problem. Models like decision tree are going to highly favor these variables here because they can immediately give them a lot of chunks of data which are pretty homogeneous, even though they may not have been so important for us here in the business. Okay, so it's very important that you look at this particular thing, guys, and you need to solve the same. So now you guys know when I do an EDA, categorical variable for target, what should I look for? Categorical variable in a predictor, what should I look for? Possible model issues. We're talking about model issues right now. What are the model issues I can look for by doing some initial diagnostics on these variables here? That is exactly what we've discussed. With the same kind of an idea, guys, let me just jump into the numerical variables part also. For numerical variables, once again, certain kinds of data will make your model become ineffective. Even in your numerical variables, guys, you need to understand for a particular pattern, okay? If that pattern is available, it will render your model to be completely useless. What is that? Very simple. For a numerical variable, I'm talking more on the predictor side, okay? We are talking about the predictor side. You need to check for something called a zero variance problem. What do you need to check for? You need to check for something called as zero variance problem. What do you mean by a zero variance problem? Very simple. I'm going to take up a data set like this. Okay, you'll have predictor variables which are numerical in nature, right? Who are the people who are numerical in nature? So I think the age of the person, the duration, campaign, previous days, these rates, everything. All of these people are numerical in nature. All we're going to do is, guys, we're going to go down here and we're going to calculate what is the variance of each of these columns here. That's all. So what are we doing? We are going back and calculating what is the variance of each and every column here. What do you see here at the bottom? These are the variances of each and every column. And the point is pretty simple. What do I have here? I have age of the person, right? Let's forget even variance. Let's do standard deviation. Even though the problem is called zero variance, let me do standard deviation. Okay. So see here, we are doing standard deviation. Now see here, guys, this is what variable is age. So you're saying I've recorded the age of all of my customers. Sounds good, right? Now you're going back and asking a question. Okay, I want to understand what is the average. So the average age of customers right now here is what? It's equal to 40. So 40 is the average age of the customers who are applying for loan. If I know that the average is 40, you're giving me that the deviations of the other people from this particular average is going to be 10.42. So what are you saying? Hey, I think more or less, mostly, all the people are going to have 40 as a value. That is going to be the central tendency. But there are other people who are not equal to 40. They're lesser than 40, they're greater than 40. There are a lot of deviations. We are asking a question, how much do you see is this particular deviation? He is saying, I've seen a deviation of 10.42. So on an average, people are far away by 10.42 units. So it means I will have what? 40.02 plus 10.42, or I will have 40 minus 10.42. So you're saying, I think most of my people are going to be between this particular bracket, 30 to 50. This is the amount of variance I have, is what you're saying. Okay, so the range of people here are going to become 29 to 50 kind of value. I mean, it'll be lesser than 29 and above 50 also, but I'm saying most of the people on an average are having a deviation of 10. So at least 50% of the population should be between 30 to 50 is what we are saying. So what do you understand? The variance is actually speaking pretty big. So I can see a lot of people who are far away from 40. So it goes up to 50, it goes down well up to 30. So we are completely convinced. So we see that there is a lot of change in the data here. I see that some customers are 25, some of them are 57, some of them are probably 55. There's a lot of change that's happening in the data. Now let's look at this one, duration. On an average, customers have spoken for 258 seconds. But I see that some of the people have spoken for an additional 259 seconds, while some of these people have spoken just for 1 second, 258 minus 259 probably just for 1 second or 0 seconds. So once again, what do you see, guys? You can see that there is a lot of variance here, right? So I can see that on an average, it has been 258 seconds, but some of these guys have gone up to 500 seconds. Some of these guys have cut the call even at 0 seconds. Once again, a massive range. Same fashion, 2.56, 2.77 looks okay. 962, 186 looks okay. 0.08, 1.57 looks okay. Now comes the problem. Do you see it? So what is he saying? He's saying on an average, the variation of unemployment rate has been what? 93.57 something. But I see at sometimes it has gone up or down by 0.57 units. So the variation here is literally minimum, guys. So what do you see? So sorry, it's consumer price index, okay? So the consumer price index on an average has been 93.57. We see that sometimes it's actually having a deviation of plus or minus 0.57. So basically we are saying that, there is not much of a change in this particular column. It has been what? Somewhere between 93 to 94 only. So the amount of variance in this particular column has not been much for us, isn't it? So just imagine something like this. You're trying to analyze a particular set of students' data. Now let us probably assume all the students' age is probably what? Something like 20 years, example. All the students are having 20 years. So only if there is a lot of change in this particular column, this variable might be important for us, isn't it? So I can ask the question, so what happens if it's 20? What happens if it's 25? What happens if it's 35? But unfortunately, all we have recorded is only people whose age is of 20 here. So I don't see a lot of variance. I don't see people with 25, 30, 35, 40 or 45. It's completely 20 here, right? There is not much of a change or not much of a variance here. So numerical variables, right? Only if they have a lot of variance on the inside, they're going to be pretty effective for us. So what is going to happen? Only if numerical variables are very, changing, there's a lot of variance, it's going to be very effective for us. But if they're not changing much, right, then it will not be very effective for us, guys. That's a very important point that you need to understand. Say for an example, I'll give you another case, okay? For an example, you're probably creating a probability of default model, let's say, okay? So in banks, probability of default models are of two types. We have TTC model, we have a PIT model. Basically, TTC means through the cycle model, okay? TTC basically means through the cycle, while PIT basically means it's point in time. So what you're actually saying is, there is a probability that one of the customer might default at the rate of 80%. And if it is a through the cycle model, right, what you're actually saying is, this is a predictive model that is using all the MEVs. MEVs like what? Unemployment rate, MEVs like consumer price index or home price index or commercial real estate index. So you're saying, hey, unemployment rate is down now, it may go up, then it may come down, it may go up, it may come down. So only when there is a lot of variation in the unemployment rate, then I can tell that the PD that I've got has gone through all the different economic cycles. So it is a number who's going through all kinds of economic cycles. It has gone up, it has come down, it has gone up, and it has come down. But on the other hand, a point in time model is a case where we say MEVs are not to be used. Why? Because we are not considering all of this seasonal or the variations that's happening here. So we are basically saying we are assuming that all the MEVs are going to be completely constant from now on. So I'm assuming that unemployment rate is going to be at 4% only. Okay. Or like consumer price index is going to be at the same value, or the number of jobless claims are going to be same. I'm assuming it is completely constant, and then I will go back and create a predictive model. It's called as a point in time PD model. So it is very important that you understand here, guys. So here you won't even use the MEVs. Why? Because you have assumed it's constant. Why do you need to include it in the model? It's not going to serve any purpose. We remove it. While here it's through the cycle, you need to capture all the variance. That is why you're including the variables in the predictive model here. That's the point, guys. So going back, if I want to analyze a data set, and if I want to make use of this age, I should have had different age values. You can't give me a single age value and ask me to go back and analyze. I don't think it's going to be very helpful for me. I can't ask questions, what happens if it's 25? What happens if it's 30? It's a completely useless variable here, actually speaking. So it is very, very important that you understand zero variance variables and you start removing them. It is a very, very important statistical issue, guys. We call it as a zero variance problem. So basically, variables which are having zero variances will typically do nothing for us. They're going to do typically nothing. I can't use those variables. They're not going to split anything for me. They're not going to help me predict what's happening. So I see a customer defaulting when employment rate is 4%, and I can also see customers are not defaulting when the same rate is at 4%. So it's not at all helpful for me. It's not helping me quantify what is the effect of somebody like that variable on the target here. So zero variance problem is a very important problem that you need to understand and you need to tackle them. Basically, you need to check what is the standard deviations of each of these people. So the way I would do is data.describe. That's it. Go back and look at the standard deviations of each of these people. That's it. Now you just have to check the variable who's not having much of a standard deviation. Just remove him. That's it. The work is done. So what do you have to do? Just go back and check each and every variable. So age is having 10.42. Duration is having 259. Euribor for a 3-month rate is what? 1.73. So just check the variables which are having standard deviations of the variance pretty close to zero. You need to remove those people. Which means in our example here, I don't think the consumer price index is going to be helpful for us at all. It's not going to be helpful. Let's do the model also. Here also, let's take it as a point to experiment it. We'll include this guy, then we'll remove this guy. Let us check what's going to happen. You'll see that the model's performance will be as it is. Or probably it might get better for removing it, in fact. So it's not going to serve any help for us. It's going to serve no purpose for us. We can in fact go back and test it also. So this is another very important statistical check, or statistical data quality check that you need to do even before committing certain modeling mistakes here. For a numerical variable, please go back and check something called as a zero variance problem. Similarly, there are more things, guys. There are more things coming. I don't think we can discuss it for today. I don't think we were able to crunch it in the 1.5 hours that we had. Next things will be something called variance inflation factor. I hope we spoke about this one, right? Variance inflation factor is something that we need to speak about, right? We need to check here. Then distributions of the individual variables is also something that you need to check here, right? And then check if there are any patterns available in the data by creating a lot of visualizations. Use the predictor and the target, create certain visuals, understand if there are any patterns in the data, use those patterns as a feature somehow, create it as a feature, feed it to the model. Because a model is like a child. He may not be able to explicitly find it, but if you are able to find certain patterns, feed it to the model. Let's check if the model is able to do better or not. So these are the different things that you need to typically do when it comes to an EDA here. Okay, so we have just kind of scratched the surface. We have started with targets and numericals, targets and predictors, them being categorical and numerical. What are the different statistical quality issues that you should be testing for? What should you do to solve them? What happens if you don't do it? So I think that's exactly what we've discussed till today. Okay. So does it sounds good, guys? The zero variance problem. You all agree with me with the zero variance problem? Why do I say that numerical variables with zero variances are going to serve no purpose? You guys agree with me? Makes sense, right? So all the concepts that we've discussed for today, is it okay, guys? Are you all feeling comfortable? Any questions till here? Clear? Perfect. Perfect. Anu says yes. Manohar said yes. Yatindra, Rakesh, Sanjay said yes. Okay. Perfect. So I think we'll kind of stop it here, guys, as we've already discussed. Okay. So for today, it's going to be an 1.5 hour session as we spoke. Okay. So I've already uploaded the yesterday's session videos and the Python code and the data set. So please do play with the Python code. Let me know if there's any kind of bottlenecks that you guys are probably facing. Okay, let me know if you have some questions on the code. Why do I do this? Why do I probably not do something like that? Come up with questions. Feel free to ask me. Okay. Okay. This thing, my OneNote notes. Okay. It's not so legible. That's why I never do it. Okay, but since you've asked if you're okay with it, I'm ready to do it. I can upload it. I never keep it pretty legible. It's like, anyways, if you're okay with it, I'll do it. And probably from the next class onwards, I'll make sure that it's properly uh, uh, what I would say is kept here so that I can pass it on to you guys. Okay, I'll do that, Arab. So, I'll do that. Okay. Okay, awesome. So thank you guys. Thanks all for joining. Let's catch up in next week's session where we'll just complete this use case and then we're going to quickly jump into decision trees. Okay, so please make sure that somehow you're catching up with all the topics that you've discussed today over this particular week. Please don't procrastinate because the next few topics are going to become more complex. Okay, so the moment you kind of have some lags here, then the rest of the topics are going to come back, hitting on you at a very fast pace. So please don't do that. The next topics from next week onwards, they are all kind of connected. Decision tree, bagging, boosting, random forest, they are all completely connected. So please make sure that till now, whatever be the topics that we have discussed, you completed by this week itself. Okay. Anyway, so thank you guys. Thanks for joining. Let's catch up in the next week. Thanks, guys. Bye.